Okay, welcome back. Did any of you get the chance yesterday to, very late, to look at the videos that I published on this morning on the YouTube? No. So where you can download the slides, I now also have links to the YouTube, to the recordings of the video. It looks a bit like a puppet show, so me running in and out of the picture, I think that will be very similar. I now try to also capture the board because I will draw something on the board. But if you have suggestions on how to improve this, or if you think it's not necessary, we could discuss it tomorrow. But please have a look at it, and I hope it's useful just as a recording of so that you can look at it again if things were unclear. So today is the second lecture on intelligent systems. Yesterday I tried to introduce a little bit what an intelligent system is, and then try to dive in directly into the matter of state space representations and search. So the idea is that you have some state the world is in, and that actions that an agent can take can get you to other states, other ways of looking at the world, and that this is a very useful tool, sort of abstraction tool, to model real-world problems and in order to find decisions that an agent can make. So what you have to do is you have to formulate the goal, you have to formulate the problem in terms of the state space abstraction. You have to define the actions that get you as a transition from one state to the other one. And then based on this abstract representation model, you can define your decision problem as a search problem in this state space. And the solution is a path from the initial state to the goal state. So today I want to move from the systematically finding all the possible solutions that we had yesterday to finding the best solution with some informed search. So where we know more about the state space itself, about the environment that the agent performs in, and about the background knowledge of what we have our decision making on. So let's look into informed search with heuristics. Before I do that, I want to briefly repeat what we did yesterday, because I think the second, sort of at the very end, it became a little bit squeezed, and you should really understand the depth first and the breadth first. So that's why I want to start with what I explained yesterday at the very end, very briefly again. So this is the algorithm that you should look into. It's called the tree search, because you start out with the root node, and then you construct the search tree. And the algorithm is very simple in principle. It's a function, tree search, that has as input the problem and the fringe. The fringe is just the sort of the programming structure, the data structure to store all the nodes in that still have to be explored. And the problem is described in some formalized way. The first step you have to do is that you have to initialize your fringe, so you put in the root state of your problem, and then you loop over the fringe as long as you reach a goal condition, or as long as there's something in the fringe. So if the fringe is empty, then you haven't found a solution. That's the first condition. The second one is if there is still something in the fringe, you take out the first element out of the fringe, and this becomes your node that you need to expand. You then expand this one node, and if it is a solution, if it satisfies the goal conditions, that's good news, you have found a path from the node to the solution. If you haven't, you have to put the newly found nodes that you have found by expansion, you have to put in the fringe in some way. So it's this insert all expand node problem fringe call, which defines your search procedure. And then we have the two things that a breadth first search is if you use a queue or a FIFO as your search procedure. And if it's a stack, you get a depth first search. So that's a sort of programming difference. So I tried to make up an example because we will look into this later. So think of some problem that you have in which you start. This is the root problem. Let's call it R. You can take different actions. Let's call it A, B. If you have A, you can maybe go to some other node, state C. You could go to D, but maybe you could also go to D here. So these are different decisions that we could take in our world, in our representation of the world, starting from some node in which we are here, and maybe there is a goal down here. Yeah, and this might be, if I talk about the Hoover, it might be moving to the right, moving to the left, moving to the right, moving to the left, doing something else, depending on what is allowed to do. Doesn't really matter what it is. We have the representation, and now the question is, how do we find a path from R to our goal using this algorithm? And what the algorithm does is, it starts with the empty fringe, and it adds the root state to it. Yeah? So that's now in the fringe. Now I take out the first element out of the fringe, and I look at what are the successors. Where can I go from the root with a transition? And in this case, in this example, I give it some arrows to make it complete. I can go from R to A, and I can go to B. Yeah? So then I put A and B in my fringe. It's not, none of them is goal condition, so I take out one, the top one, and I look what are the options that I have to go. I can go to C, I can go to D, so I add them to my fringe. Here I've made the decision to add them at the bottom, so this is the Q model. I could have also added them to the bottom, to the top, and then it would have been B, C, then I should start down here, so it should be B, C, D. So that one is breadth first search, and this one is depth first search. Yeah? And then I take out the top one again, B, and I add the one possible successor, so I can't go from B to D, I just add D to the fringe, which is where it is already, so I probably don't have to add it to avoid duplication. So that would be in the breadth first search. If I use the depth first search, I remove the top, so that would be D, and I just add the next one to the top of the list, top of the stack. And then, magically, I found my solution here with one step earlier than my breadth first search. Yeah? So if I do breadth first search, then I do this, and this. So that's 5 different options. And if I do depth first search, I do this, and this, and I found the solution. I just have to store this one at the corner. Yeah? So that is the algorithm. Very simple, easily seen, and it's only the data structure that really makes the search behavior completely different. And then we have properties that we can assign to these algorithms. such as completeness. Will the algorithm always finish? And if you consider, for example, an example where we have this behavior, and you would apply the depth first search, even if we are unlucky, then it might be that we add from R, we add A, and we add R again, and we add A again, and we have an infinite loop. We have an infinite search tree. Yeah? Because my search algorithm will basically go always round and round and round and round. So that's the bad news. Depth first search is not complete. It will not, sometimes it will not find an answer. Breadth first search is in principle complete. There are some examples where if you have sort of pathological examples where you have infinitely many choices. So if you can pick at random rational number and that is your decision step, then you have infinitely many, uncountably many choices even, and then obviously you can't have a decision procedure for it because there are uncountably many options you have. So then you would never find the solution this way. The time complexity is the same. In the worst case, you have to look through all the structure, to all the problem space, but the space that you need, the memory that you need for running this algorithm is far better when you use this one, because you only have, in principle, you keep only this path in memory with this one around, whereas in breadth first search you need almost all of the data structure in several copies in your memory. So remember that when we talked about the Schnapsen, already the relatively simple game has, if you run in the second phase, if you have 5 cards and the number reduces, we have 15,000 different nodes that we can walk through, and it would be really stupid to go through all the states systematically without taking any knowledge into account. And what you can see here is that if you start with the ace, the left-hand side card, this is a good choice because your opponent, or in this case, you don't have an opponent, but in this case, the other hand has to play the 10 of the same color. But this is some kind of informed choice. Is nice if you start out with the ace of spades. Now, suppose that you start out from the other side, that you start out from the king of hearts. Then basically, your opponent might have to play the ace of hearts. So in a way, there is knowledge involved where we say it would be better to start with a higher card, for example, or a card where I have all the colors, a card which is trump. So there are some heuristics, there's some knowledge about the game, there's knowledge about the states that we can use to inform the search. So basically what we did here is we treat all the nodes the same. And now in informed search, we say, but we want this node to be far higher. Node D is the one that we want to have immediately up as soon as we can. Because here we were lucky in this search because we started with, in this one, we started with D. But that was just lucky because we could have also had C. It was also in the list, in the stack. So now the question is, can we give some ordering to the fringe? And this is basically what informed search does for you. Why this order? Why did we choose this order as I did? If you take a different order of the states in your fringe, you get a different search. And this is absolutely needed if you want to do search in real life problems. So the approach with informed search is called best first search. So we don't do sort of the breadth of the tree or the depth of a path. No, we look for the best node. And that is sort of the general framework of how we deal with these kind of problems, state space problems, and namely looking at an ordering on the nodes, and always put the most promising one at the top of the fringe. Then, of course, the question is, how do we decide which one is the most promising node? Because in a way, this is exactly what we want to find. We want to find out that this is the best, most promising path. So, of course, this is the most promising next node, this is the most promising next node, and so forth. So the best heuristics to apply would be the result of my algorithm, which is obviously not working because the complexity of this calculation is so high that it would make the whole point meaningless of using a heuristic. So we need a quick win evaluation function that tells us the chances that this one is good is higher than the chances of this one. And in a way, we need an evaluation function that tells us node A is closer to this one, than, for example, node R. So in a way, we need a distance function between nodes in our search and the goal states. And then, as I said, the fringe is just the queue, or sorted by a decreasing order of desirability. So we start with as a top position, we start as the most desirable object because we evaluate it, we think, we guess that it is really the most promising node. And then we have the lesser, and the further we go in the queue. And now the rest of, in principle, the algorithms that I will show in the first half are just special cases or implementations of this best first search, and also some of the classical algorithms. A star is sort of the AI algorithm that has been developed in the last century. I will discuss on Thursday in the lecture as well. Yeah? In principle, the A star algorithm is nothing else but a best first search algorithm with some special properties. As I said, to be discussed on Thursday. So the big question here is, how can I make a good estimation of the distance of a node from the solution? And that's the problem of a heuristic. So how can I come up with good heuristics that tells me this state is better than another state in terms of being closer to the solution? You can think of it we'll see that in a minute, you can think of it in a chessboard position. If you give two chessboard positions to humans and you ask them which one is better, most of the good chess players can tell you, oh yeah, this one is better for me as a white player. Why is that the case? Because they have means of counting. They haven't done all the search through the end, but they know, for example, that if I have more of the valuable figures, then my position is better. So if I have the queen and black doesn't have the queen, then my position is better. In some cases. I see you frown. So depending on what the adversary has. So in a way, whatever we as humans do perform some intelligent tasks, the first thing we do is sort of do some guesswork. And this guesswork is based on experience, is based on some implicit facts. And the heuristics is the trick to make this explicit. So a heuristic function is a rule of thumb, a simplification, or an educated guess that reduces or limits the search for solutions in domains that are difficult or poorly understood. So usually in AI, you see this h of n, which is the heuristic function of a node in a state space, which is the estimated cost of the cheapest path from node n to the goal node. So it's an estimate. It's an estimate where we as humans can really put in our knowledge in an abstract mathematical way. Where obviously the intuition is that when we've achieved the goal, when we are at the goal position, the distance should be nil. So finding a good heuristics means educated guessing. So if you have complete knowledge, these heuristics, they are difficult. You might be able to have a heuristic, namely calculated via exhaustive search. But that's far too expensive, because then you spend basically the time to search for your heuristic. You do the search, and then you don't need the heuristics anymore, because you found already your solution. So using the complete knowledge for calculating the heuristics is usually a very bad idea, because it gives you the perfect heuristics, but it takes too long to calculate it. So you want something that's very quick, that's sort of one eyelash, and you see, okay, this one is better than this one. And partial knowledge, human expertise, educated guessing is exactly what we need here. Mind you, heuristics can be extremely wrong, and we'll see some of them, and we see some problems with this approach. So here is an example for these maze puzzles where you can move tiles. So the goal here is to have, on the left top corner, you have the 1, and then you have the numbers in a clockwise circle. So we have 2, 3, 4, 5, 6, 7, 8. So that's the solution. And now the question is, what are the moves you can make? Obviously, moving the number 1 down or moving the number 7 to the right. That are the two options that you have. So which one is better? And then the question is, how can I calculate a heuristics that tells me that the position that I get into when I move the 1 down or when I move the 7 to the right, which one gets me to a state with a better heuristic value? And one example, what you could do is just counting the number of incorrectly placed tiles. So how many are there? So it's the 2 is incorrect, the 8 is incorrect, the 3 is correct, the 4, 5 is correct, the 7 is incorrect, the 6 is incorrect. So we have in total 5 tiles that are not correct.
What comes the black tile? The black tile?
Gets in the middle.
So it's also in the incorrect position, right?
That depends on the definition of the problem. It's a very good question. So it depends on whether you consider the things have to be in the right. It depends on the definition of your heuristics. Yeah?
Would it make sense considering this problem? 3, 4, 5 is correct because eliminate literally that side of the problem.
It's a very interesting point that was made, that this side of the game is sort of correct. So wouldn't it make sense to look at this only? The price you pay for this is that you change your representation structure based on knowledge for a specific game. So basically, you have a specific game, and you need to re-implement your whole game. So in that sense, yes, it makes sense, but no, it doesn't make sense, because you can't. It makes sense in the human intelligence, but it really defines a new state space problem, new algorithm you would, and we're looking for generic algorithms here. So it's a generic method. So the point is, can we now, if we move now the 1 down, do we get a better position? The heuristic value remains the same, because the 1 is still incorrect. The 7, if it goes to the right, is now in the right position. So moving the 7 down, moving the 7 to the right. Yeah, moving the 7 to the right gives us, I want to confuse me, that's right for me. Oh, it's left, sorry, yes. To the left. Okay, moving the 7 to the left reduces the heuristic value. So this position is better. Yeah? So it would make sense, according to this heuristics, to put the state where the 7 is on the left, on top of the position where the 1 is down, because it has a better heuristic value. And better means smaller. So the smaller the heuristic value is, the closer we are to the goal. Okay, so here's another one. Sum of the distance of tiles from the goal position. It's called the Manhattan distance. You know why it's called the Manhattan distance? Because Manhattan is organized like this. So if you want to go from this point to this point, you count the blocks that you take. 1, 2, 3, 4, 5. Yeah, that's the Manhattan distance. So let's count the Manhattan distance here. So this one would be 1, this one would be 2, this one is, these are correct, this one would be 1, 2, 1, and 1. So I counted, I think, 7, but here it says 6. I think you get the general idea. I must have miscounted somewhere. Yeah. So now the question is, if we move the 7 to the left, does it improve? If we move the 1 down, does it improve? Again, if you move the 1 down, it even worsens your heuristic value because the 1 now has a higher distance from the point it should be. So your heuristic value goes 1 up. And if you move the 7 to the right, to the left position, to the right position here, to the left, then the heuristic value improves, so it gets down. So this different heuristics gives different values, different estimate. But in this case, it gives the same, it would suggest the same decision. So here's another heuristics, and that is twice the number of direct switches that help you to get to the goal position. So which of the things could we switch directly so that they would be in a position? The answer is none. So the heuristic says twice the number of direct switches is 0, and can already sense it coming that this is not the most clever heuristics ever invented, because it doesn't convey any information that really is useful here. So, as I said, heuristics can be very wrong, but that makes it interesting in these in the implementation of these intelligent agents to really think very carefully about the heuristics, and that's part of your research that you have to do. So the question is, if you get a hand in a Schnapsen game, can you tell me which hand is better? So if you play a card, do you end up in a state that has a better chance of winning the game? And that's a very, very tricky one, and that's why I think I suggested also think of play the game, look at it, get a bit of experience, because this is where the human knowledge comes in and where the power of these heuristics lie. Some simple properties of heuristics, or some way of writing it down, we can sort of order heuristics according to the informativeness that it has. So if we know H star n, which is usually the perfect heuristic, so that gives you the perfect estimation of the different distance, then a heuristic I find is perfect if it has exactly the value that it should have according to the definition of the distance between the goal and the state I'm in. The trivial heuristic is the one that always gives 0, so that's not really helpful. And anything in the middle is, for every node, the value of the one is always smaller than of the other one. And that says that H2, which is closer in all this estimation to the proper value, is more informed than the other one. And it means that H2 is usually more expensive to calculate, but it helps you find more the path more easily. So let's see how this works in a more realistic scenario, and that's our traveling from Romania from Arad in Romania to Bucharest. And the information we have on the first hand is our state space with the distances and the costs of travel from one state to another. And the other information we have up there, which might be a bit difficult to read, but you can trust me on the details here. That's the B-line distance between the city and Bucharest. So it's the straight line distance, as it's called here, SLD, straight line distance, or B-line distance. It's the line as a bee would fly if it would go from Arad to Bucharest, and that is 366 kilometers. This is extra information that we get from somewhere else. It's not information that is in our problem description. So the problem description is just the rail network or the motorway network from Romania. It's extra information that we might find on the internet or that we have in our heads or whatever. And we can use this information, this extra information, to estimate how long it will take us to travel from Arad to Bucharest using only the train network or whatever way we go. And then the idea is that we always choose to go to a place which is closer with the B-line distance to Bucharest. And that gives us what's called a greedy algorithm. You always start with the best solution, the one that is closest to the solution. The algorithms that I will show on Thursday are also best first algorithms, but they don't necessarily, the best one doesn't need to be the one that is the closest according to your heuristics. But I'll get into that on Thursday. For the moment, the only thing you need to understand is that we now build our fringe again, but now with information that comes from these heuristic values from our straight line distance heuristics that we get somewhere. And we always take the one that is closest to the goal to start to evaluate on. So that gives us our ordering of our fringe according to this heuristics. So here it's hopefully a bit more readable. So we are in Arad, and now we have the choice to go to either to Zerind or to Sibiu or to Timisoara. So the three. Yeah. So greedy search will now take all these three nodes and order them according to the direct distance to Bucharest. So we have Zerind, which is 374. We have Sibiu, which is 253, and Timisoara, which is 329. So we have the ordering. Sorry. Zerind is the furthest away. Then we have Timisoara. And we have Sibiu. Yeah? The best first search algorithm suggests that we take now Sibiu as the first one we explore further. So we go from Sibiu to either Fagaras or Râmnicu Vâlcea or something like that.
Or Oradea, which is also...
Oh, Oradea, yeah. And we can even go back to Arad.
Yes.
Very good point, thanks.
But you could probably filter that option out because...
Exactly, yes. So that would be a loop detection check that you would put in. So these are the four options that we have. So now, how do we order them? How do we put them in our list? Let's look. Fagaras is 167 and Râmnicu Vâlcea is 193. So Fagaras would be the first one. And then Râmnicu Vâlcea. And then we need to sort of align Oradea sits between Zerind and Timisoara.
No, it's actually worse than both of them.
Is it? Oh yeah, it's worse, sorry. So it goes to the end. And the other one is back to Arad. And that one is now in between those two. So here we have Arad. Yeah? So after expansion of the node CPU, we have a new fringe in this order. So we take out the first one again, and we look at what are the successes, and that's Bucharest. So we found the solution. Yeah? Okay, so here's the example drawn out. You start with Arad, We use greedy search, so we look at what is closest to the goal. We look at all the three options that there are, Sibiu, Timisoara, and Zerent. The best one, the closest one to Bucharest is Sibiu, so we expand that one further. Now we have these 6 nodes in our fringe, and we know that the next one is Făgăraș to explore, and we expand it. We could go back to Sibiu, but that's further away, and Bucharest is a solution. So, we've reached the goal, but actually, interestingly enough, we didn't find an optimal solution. We didn't find the shortest path. Because if we would have gone from Arad to Sibiu, if you look at here, so Făgăraș, Bucharest is 310 kilometers, and Sibiu, Bucharest via these 2 places is slightly less.
278.
278, I hear from anybody less or more? Okay, 278, so this one is shorter, but our algorithm wouldn't find it, yeah? So basically we found an algorithm that gives us a good suggestion for a path from Arad to Bucharest, but not the shortest one. Again, I have to sort of make this week really full of tension, and I will give you an algorithm on Thursday which calculates the optimal solution. And that's the famous A-star algorithm of AR. For now, yeah?
Why does the list say Făgăraș 176, but in the graph it's the distance between Făgăraș and Bucharest is 211?
Say it again, sorry.
Distance in the graph between Făgăraș and Bucharest is 211, if I see it correctly.
Because this is the train connection, or the motorway. And the motorway will probably do this. Yeah? And in the table, we have the B-line distance. So what the train does is an abstraction over the real estate. It might have mountain tops and lefts and rights. And the B-line distance is the shortest one. And basically the trick is, that's a very good suggestion, that if you have a heuristics that has a very good estimation of the distance, then you can come up with an algorithm that's optimal. So we get to that on Thursday. But that's why we say this estimate of the heuristics is independent of the problem description that we have. Because this is an abstraction over traveling by road or by train, and it will take detours and so forth, so it will take longer. So that was the greedy search, which always looks at the one that is actually the closest to the goal. Now we have a special case of greedy best first search, namely where we forget everything that we've seen. So here I gave you the fringe as this list of 8 states. We always sort of had the opportunity to go back. But if you do best first search greedy way with only one element in memory, it's basically you look what's the best state and you forget the rest, and you're still in your place. So in the hill climbing example for this travel from Arad to Bucharest, it's actually, you get the same result. You go from Arad, Sibiu, Făgăraș, Bucharest, but you forget everything else. And that is obviously very appealing in terms of computation property, because you only have one state in memory, the one you're in. You look at what are the options, you walk it, and then you forget where you are. So the result in this case would be the same, apart from the fact that it is far more far less expensive to calculate with hill climbing. The problem is that this is not really a good way to always find a solution, because if the heuristics is a little bit off, then it might lead you to some local optima, where you are in a place where you can't get any closer to the goal, but you're not at the goal. So here I give you an example of a stupid heuristics, as you wish. And that is basically, the heuristics is 9, which is the number of 2, 4, 6, 8, 9 letters, minus the length of the name of the place. Of course, you see, this has nothing to do with the distance to the city of Bucharest. It has something to do with the distance of the spelling of the name of the letters to Bucharest, but it's completely useless information for our purpose of finding the goal here. But if you apply this heuristics, you get, and you start, that was bad news. My computer thought. I was talking to Lol, apparently. It was break, time for a break, I see. So if you are in Arad, you apply this heuristics, and then you see that Arad, the value of the heuristic is 5. Timisoara I can't count, but I think it's 1. Gerind is 2, 4, 6 is 3. So you would go to Timisoara, that is the shortest one. This is the best value. But then you can't improve anymore, because you have already, let me count, 4, 5, 6, 7, 8, 9. Yes, heuristics is nil. The value is nil, you are perfect. You can't get any better. If you've forgotten everything else, you know that this is worse, and Arad is worse as well, so you're stuck. And you can say, okay, I couldn't find a solution, because I'm as good as it gets. My suggestion is go to Timisoara, and then I don't know further. That is what hill climbing would give you. Yeah? So that's why it usually is good to have more information about the nodes and not throw away everything. But hill climbing is a very powerful means. You have a very fast search through the space of possible options. Het wordt vervolgd. It will be continued on Thursday, where we look at beam search, which is basically an idea of not taking all nodes in the fringe, but take a subset of the nodes in the fringe. And if you do this in a hill climbing way, in an intelligent way, then basically what you get is a kind of evolutionary algorithm. So that's quite interesting. The A algorithm is one that not only looks at the distance between the node we are in and the goal, but also at the distance between the point where we're in and the distance we have already traveled. So it takes into account the whole path. And A star is a special case of A. So first, this is now, I think, enough on systematic search. The algorithm basically on the fringe. Now with informed information, with heuristics. Now let's move to the adversarial games, adversarial search state spaces where you try to optimize your goal, get to a place as quickly as you can, and someone else tries to do something different. And the most extreme case is if you play a game, you want to win according to one criteria, and the other person wants you to lose according to the same criteria. And this is why we're looking into the games, so that you can start with the practical work. Today we're looking at the min-max algorithm. Tomorrow we're doing a more efficient version of the min-max, plus Monte Carlo sampling, some statistical approaches, because our search space is so big. So, and then we have to do some modeling about Schnapsen in the next time to do. So now it's time for a break. Let's start at 12 again, please.